is Kevin, and today I'll be walking you through the lab we conducted on the motion of a pendulum. The question we can be asking ourselves for this lab is, how can we predict the motion of objects swinging back and forth on a string? Here are the conditions of the experiment I did to try to answer this question. First, I created a homemade pendulum consisting of an iron ball hanging from a string and recorded its motion string and tracked its x and y position coordinates using tracker. I then coded a computational model of the pendulum using glowstrip, and then I finally compared my two results. So to answer this question, I largely based my calculation on two fundamental principles: the momentum principle, Newton's second law, and energy principle, the first law of thermodynamics. I also made a number of assumptions. The string I use can be considered as extremely stiff string, and therefore the tension force can be modeled as a spring force. The string's mass is negligible, so I only consider system's mass to be only the iron ball's mass. As I applied Newton's second law, I assumed that the only forces on the system are the gravitational force and tension force. Finally, the system is isolated from its surroundings, so there's no work done on the system. So in the next slides, I will be going into a more in-depth overview of this lab and experiment to answer the question. Note that the iron ball will be modeled as a significantly lighter object to allow our glow-stick program to be fine-tuned towards a small delta t in small increments. So let's get into running the glow-stick program. In the system's properties and initial conditions, I simply define the mass of the object in initial position based on tracker data and its initial velocity, which is 0 since it's released from rest. Next, I define useful constants such as the gravitational force g, the spring's stiffness k subscript s, and the spring's relaxed length L naught, and L and L hat vectors, as well as the spring stretch s. Also define three energies that spring mass system has: kinetic energy k, gravitational potential energy u subscript g, and total energy e. In my calculation loop, you will see that I set the initial energies and define my net force as the sum of a gravitational force and a spring force. I will then also apply the momentum principle to update the object's velocity and position. From there, I will also update the energies and calculate the energy changes, as you can see here. Finally, to run the program, I will include a CSV file with the positions data I have included from Tracker, which will be seen later in the visualizations of its impact. So here are some of the observations in this slide, and some of the other graphs will be shown in the following slides. So let's talk about observations I made from my code. When I run my code, it represents the motion of the observed model as a red ball and that of the computational model as a blue ball, as well as tracks the blue system path. We notice that the computational model starts to be well behind, otherwise a lot slower than the observed model. This can be illustrated by these x and y position versus time graphs. The two curves are identical. In fact, because the blue ball is much slower, it completes fewer repetitions of movement in the red ball. We also have the energy versus time graph plotting total change in energy delta E in orange, and the change in kinetic energy delta K in blue, and the change in gravitational potential energy in delta U little g in red. We notice that at any moment in time, delta E is very close to zero, and then delta K kinetic energy and the change in gravitational energy varies between positive and negative signs. Regardless, the change in kinetic energy and the change in gravitational energy do cancel out to add up to zero, which is nearly zero, because we know work done is zero, and thus the total energy system is simply translated and converted between one another. So now let's discuss some of our observations. First, we'll answer a few questions. First of all, for this model system, is the energy principle satisfied? Well, this energy graph comes quite close to confirming that the energy principle. As we can see, there are discrepancies. On first hand, we see down the first graph that the change in energy is equivalent to the change in kinetic energy plus the change in gravitational potential energy. So this confirms that there are no energy transfers between the system and its surroundings, and the total amount of energy of the system remains close to constant. So next, is the momentum principle satisfied? The positions for times by x and y for both the observed model and computational model don't match up. This will mean that another force is acting on the system, so the net force I chose is incorrect. Now let's also talk a little about periods of oscillation. So here are the x and y position periods for both models. As the system goes through output, both of the computational model's periods are longer than those of the observed model. In both cases, though, the x period is twice as long as the y period, and this is logical because when you think about it, it takes the pendulum one full swing back and forth to return to its initial x position, whereas it only takes one single swing to return to the initial y position. So now let's talk about conclusion. I would like to discuss some explanation to the discrepancies we observed and possible improvements in our model. So some of the discrepancies converge from the fact that energy graphs mostly origin from the fact that the spring force, unfortunately, is not a perfect model and thus may have some impact on tension force. There is still a small stretch of spring, as small as may be, and this is why the total unit system of all situated on zero. Also, the larger amplitude of the pendulum is the more complex the equation of its motion gets. Therefore, perhaps if I swung the iron ball on a shorter string, my position versus time graph might have matched up better. So thank you guys for watching, and I hope you enjoyed this last lab's explanation.